So vertical work and gravitational potential energy, again, we have an estimate. We need to know what that means. So we want to know how much work is done when a student climbs the stairs from the ground to the first story. So we have a student here like so, and they end up here. And we know this is 1 story. Well, the work done is going to be the average force times the distance. Now, the student is climbing up the stairs, as we've seen before. This vertical work, we have the force of gravity and we have the force applied. Well, we said a key piece of that is that it's at constant velocity, so these 4 forces are balanced. The force of gravity is mg, so we have mg, and this distance is the height, which is the potential energy formula. So we've got this mg, the force of gravity of a student. Well, all of you know what your force of gravity is. You've done a lab on this already. So you might say the force of gravity, yours, is 700 newtons. That's a value you would come up with. And the height, well, let's see the height here. We know hip height is 1 meter. So we might ask ourselves, how many hip heights is it? We could start out by saying, is it 1? No, it's definitely more than 1 hip height. 2 might be about 6 feet. 3 might be about 9 feet. 4 might be about 12 feet. So probably a good answer here would be 3 or 4 meters. I'm going to use 4 meters. And so 4 times 700 is about 2,800. So 2,800 joules is the estimate of about how much work. We could even say, which is about 3,000 joules. So that's about how much work would be done. All right, so next we have 4 persons entering an elevator. One, 2, 3, 4. Their combined mass is this. They travel from the 3rd to the 7th floors of their building. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3. We're going from the 3rd floor to the 7th. 4, 5, 6, 7. 1, 2, 3, 4 floors. And it's a 16.4 meter change in elevation, in altitude, so 16.4 meters. What is the amount of vertical work done by the elevator? Well, that vertical work, which we know is equal to the change in potential energy, is mass times the gravity times the change in height. So the mass we know is 336.7. We know the force, the gravitational field strength is 9.80665, and the height is 16.4 meters. So multiplying those out, we get 336.7 times 9.80665 times 16.4, which is 54,151.1445 joules. So that is the work, and that is equal to the change in gravitational potential energy. Now looking at the significant digits, we have 4, 6, and 3. 3, 6, and 4. So our final answer can have 3 in it. So those 3 there, this 5 would cause this to round up. And what we want to write is 54,200, but we can only express it to 2 digits. So we have to write that in scientific notation. That is 1, 2, 3, 4. So 5.42 times 10 to the 4th joules. That is the work done. The next question, we have Ryan dragging a box up a long 15-meter ramp. So we've got a 15-meter ramp, and the box is 13 kilograms, and the height is 2 meters higher. The force applied is 24 newtons. How much work did he do pulling it up the ramp? Well, that work is the force times the distance, and the force is 24, and the distance is 15. And that works out to be 360 joules. Now, we have 2 digits here, 2 digits here, so we can only have 2 digits there. Writing this number in scientific notation, we get 3.6 times 10 to the second joules. That's how much work the person did dragging it up the ramp. Now, Isaac comes in and lifts the box, identical box, straight up to the same height. What was the gain in gravitational potential energy? So the change in gravitational potential energy is mass times the gravitational field strength times the height. The mass is 13, gravitational field strength 9.80665, and the change in height is 2.0 meters. So 13 times 9.80665 times 2 gives us 254.9729 joules. Now we're looking at our significant digits. This has 2, this has 6, this has 2. So 2, 6, 2. So our final answer can only have 2 significant digits. The 4 would not cause the 5 to round up, so we're left with 2.5 times 10, 2, times 10 to the second joules, the change in gravitational potential energy. So we get to the next question, question 5, and we're told that we want to explain why the work are not the same. So we had Ryan dragging it up here, and it was 360 joules, and we had Isaac lifting it up, 250 joules. So clearly there's a lot less work involved in lifting this up than there is in dragging it this distance. But what we know is that it should be the same amount of work. In both cases, the work done against gravity is the same. But the problem is, in dragging this box, the bottom of the box is in contact with the ramp, and there's friction. So when Ryan is doing his work, dragging it up the hill, some of the work he does is against gravity, and some of it is done against friction. So, what are we going to say? For both, the work done against gravity is the same. However, since Ryan is dragging the box, there is also work being done against friction. When Ryan is doing the same work against gravity, plus more work against friction, it means he does more total work. And we could put a number in here, 360 versus 250 joules. And we could, the work against gravity, we could say the same as 250 joules. That's how we put in our evidence with our claim, evidence, and reasoning. Our evidence is the number. However, since dragging the box, there's also work being done against friction, which we can figure out is 90 joules. Because, 110 joules. because we have 250 plus the work against friction is 360. So the work against friction is 110 joules. So now we put in our evidence and reasoning as well.